Hello. Yeah. I hope you can hear me. Okay, so first I would like to thank Sanjib for organizing this beautiful conference, and I have enjoyed. It has been very nice, and I have listened to many beautiful talks. I have learned many things, and also it's always a very happy moment to give a lecture in this seminar in this room, in this hall, because I gave my thesis seminar in this hall. so, so I'm giving here another talk. Okay, so I'll talk about hard rod gas and quasi-particle motion and correlations in this. So I'll mainly talk about results from these two papers, and also I'll mention some results from these two papers, and these are done in collaboration with many people. Meenal and Seema were current graduate students at ICTS. Sahil was a graduate student, now is a postdoc in University of Luxembourg. Indranil is a postdoc. So Seema and Indranil are in the audience, and also collaboration with Abhishek and Herbert. Okay, so hard rod is in one dimension. A gas of hard rod is a simple interacting system. So this is the Hamiltonian, and they are like extended hard core objects. So they are interacting via hardcore interaction, and this model has been used widely to understand various equilibrium phenomena because it's a simple interacting model of gas in one dimension. The dynamics is very simple. So in between collision, two rods just move ballistically, and in collision they just exchange velocities like this. And these are trajectories of such rod, and so this is the gas. And one can solve for these trajectories exactly by using a mapping to hard point gas. So given a hard rod configuration, you can you can construct another configuration by doing this transformation. So basically what you do is basically you remove all the inaccessible spaces between rods, and you get point particle configurations, and you keep the velocities, and then you get another configuration which is small xi, and this is this typesetting x. And then these point particles, they just you can just move them ballistically, and once you evolve them, then you get the final hard point coordinates, and then again you use another transformation, opposite transformation here. It was you just remove the spaces, but now you add the spaces again, and you get hard rod configurations. So, and that's how you can solve the microscopic dynamics completely. So that's why it's an interesting, simple example of interacting integrable systems in one dimension, and it has extensive number of local conserved quantities. As I said, that at collision, two hard rods exchange velocities, and they do not mix the velocities. So that's why you can actually choose conserved quantities like this, which are like moments of the velocities. So you can just sum the velocity power alpha and alpha 1, 2, 3, even. So these are conserved quantities. You can choose such conserved quantities. In fact, any functions of this will also be conserved quantities. Okay, so and because it's a simple example of interacting integral system and short range interacting, so they have recently drawn a lot of interest because in the recent times there is a huge development of generalized hydrodynamics, which describes large scale motion in integrable systems in one dimension. And let me briefly tell you in 2 slides about this integrable systems ideas. So these are systems which have extensive number of local conservation laws, and they fail to formalize to Gibbs state, and it is kind of believed that they formalize to generalized Gibbs state. And let me tell you what is generalized Gibbs state by comparing it to the non-integrable systems. So non-integral systems, you have a few conserved quantities like commonly the number, energy, momentum, and the stressing states are described by Gibbs ensemble, which are characterized by these few conserved quantities. Whereas in the integral systems, you have extensive number of such conserved quantities, and you have to incorporate all of them to describe the stressing state, and which is a generalization of this Gibbs ensemble by incorporating all of them with the corresponding chemical potentials. And inhomogeneous dynamical states in this case is described by hydrodynamic equations, which are few corresponding to this conserved quantities, the corresponding densities. And in this case, this generalizes to this. For each of these conserved quantities, you have a conserved density and the corresponding current, and you have continuity equations, and that's how you write down this extensive set of equations as conserved hydrodynamics. However, this is not very useful, such aerodynamics, because you have to handle with many such equations. So there is a convenient way to express the aerodynamics in terms of the densities of quasi-particles. This is a kind of a right basis that people have. These two papers are found in quantum integrable systems, and this is like a collisionless Boltzmann equation where you have some densities of quasi-particles, and they are moving with some effective velocities, which is similar to free particle equations. So suppose you have free particles with velocities v, then you have such equation. It is similar to this equation. Okay, and once you have this quantity, then you can write down all the conserved quantities as integrals of these equations, and such integrals lets you kind of identify these local conserved densities and the corresponding currents. Here I write once again, and so that's why you actually have these equations also incorporated in this equation. Okay, so for what are the quasi-particles for hard rods? I said that these densities are for quasi-particles. What are the quasi-particles for hard rods? To identify that, let us first compare the dynamics of hard rods with hard point gas, which is basically the rod length goes to 0 case. So here also the dynamics is very simple, that they get reflected of each other, and the velocities get exchanged at the collision. But if you, instead of exchanging the velocities, if you exchange the label, so let's say exchange the color at the collision, then you get like a non-interacting particle, which is basically doesn't see each other, it just pass through, and you get this kind of trajectories. These are quasi-particles, and in this case, these quasi-particles are non-interacting. And if you do the same thing for rods, and instead of exchanging the velocities, if you exchange the colors, again you get quasi-particles. So this red rod's trajectory is one quasi-particle, and this black rod trajectory is another quasi-particle. But you see that these are now interacting, because at collision, this quasi-particle will jump in displacement. So if it did not interact with the other quasi-particle, it would have come here, but because of the interaction, it has a jump in this direction. Similarly, it also has a jump in this direction. So you get quasi-particles, but interacting quasi-particles in this case. So these are actual rod trajectories, but you can represent this gas by also quasi-particle trajectories by the similar construction that I described last slide. So gas of hard rods you can think of as gas of interacting quasi-particles, and this picture is used in the aerodynamic description. So you can write down densities of such quasi-particles, phase space densities of such quasi-particles. Okay, and then once again one gets such an aerodynamic equation. I don't go into the details how you get this thing, but here you see that if A is 0, you get back the free particle equation, because V effective is just become V. But because A is non-zero, and at each collision they get extra jump, so there is an extra displacement, and because of this the velocity is not just bare velocity, it gets modified, and that's how you get such an equation. Okay, good. So in this setup, this is given this small introduction. Let me tell you the questions that I want to address is, so I want to basically understand the motion of such quasi-particles. How does a quasi-particle in hard rod gas move, given the initial conditions are chosen from some ensembles. I'll describe what are the initial conditions that I'll consider. And then I'll also talk about what is the aerodynamic correlation between densities of this quasi-particle in different locations in phase space. And also what is the role of these aerodynamic correlations into the quasi-particle dynamics. So these are the questions that I want to address. So first, I'll talk about the initial states. Of course, you have to prepare the system in some states. That you choose the initial configurations of the rods, positions, and the velocities from some distribution. And this is one initial condition that has been considered in the literature. So here you just choose the position and the velocities of the rods independently, but you respect this constraint that no two rods can overlap. That's the initial condition. But furthermore, you choose this function in such a way that any densities that you compute from this distribution initially has a scale of inhomogeneity which is L. Okay, that's how you can choose. This is one set of initial condition. So I denote this initial condition IC rod, because I choose the configurations of the positions directly. There is another type of initial condition that also is considered in the literature. It has been actually considered previously by Lebowitz, Parkas, and Sykes. So here you basically choose the positions in the point particle. So you choose the positions of the point particles in from IID distributions, and then order them and then transform to rod positions. So you first choose them and then order them, and then you can transform, and you get a hard rod configuration. And that's how also you can choose the initial configurations of the hard rods. And once again, you can actually introduce a scale, inhomogeneity scale, to create profiles initially over a length scale L. Okay, and I denote this initial configurations point to rod. Okay, so first let me focus on this question: how does a quasi-particle in hard rod gas move? And I'll try to answer this question for this initial configuration, but some of the results can also be generalized to this initial configuration. But the computations are much more involved and difficult, so I'll not go into that. But if you're interested, I can tell you. Okay, so first let us consider the simple case, which is the initial condition is homogeneous. So that the scale of inhomogeneity is infinity. So it's a homogeneous case. And this is the problem where you have a homogeneously filled box with rods, and the velocities are chosen from Maxwell distribution, and you have a particle of velocity v naught at the origin. And you ask, how does this particle move as the particles are moving and following the hard rod dynamics? Okay. So once again, the simple case is for the point particle. If the rod length is 0, of course this particle will not see the presence of other particles, and in t time it will just go there. And the distribution, the position distribution will be just the delta function if it was at the origin. But this will not be true for hard rods, because hard rod, for hard rod gas, the quasi-particles move randomly, because at each collision they jump by amount A, and they can jump plus A and minus A depending on the collision that it gets from their right or left. Okay, but on an average it will move by an effective velocity, and in this case, because it's a homogeneous background, effective velocity is fixed. So on an average it will just go there. However, if you simulate, you see that of course on an average the density profile for or the probability density of this particle moves, has a peak which moves with v effective t, but it has a spread, and it actually has a diffusive scaling. If you scale it, all the curves collapse, and one can find out the scaling curve, and it actually is a Gaussian, and one can find out this Gaussian by solving the hydrodynamic equation with the Navier-Stokes correction, which I didn't tell you about, but one can actually add Navier-Stokes correction for this hard rod gas, and one can solve this equation by linearized version of this, and one gets this solution, and that is what is plotted, and it actually agrees very well. And this solution was also obtained by Lebowitz, Parkas, and Sykes from a kinetic theory point of view. We also obtained this same solution, but from a microscopic approach. So I'll talk about this microscopic approach in little bit more detail. Okay, so this is the microscopic structure. So this was the position of the rod at 0 at time t equal to 0, and in time t it will move v naught t if it did not interact with any other rods. But because if it gets collided with other particles, there will be plus A every time it gets collided with another rod which comes from right. It will jump on the right side by plus A, and it gets collided with a rod which comes from the left. It jumps by minus A. So that's why it will be A times the number of collisions that comes from the right to left, and then minus number of collisions from left to right. And for a homogeneous initial configuration, to find out the statistics, you need to find out the joint distribution of these two numbers. And for a homogeneous initial condition, and in this initial condition, actually we don't need homogeneous for even for inhomogeneous case also. For such initial configurations, this two joint distribution becomes independent in its product form, and they are independent Poisson distribution for large n. And one can use this fact, and easily one can compute this property and compute the distribution of x. and one gets this Gaussian distribution. And this suggests that maybe the tracer rod seems to move like a Brownian particle, right? And but the question is there any further evidence? For that thing, what we did, we tried to compute the two-time correlation, autocorrelation. So this tracer rod reaches x1 at time t1, it reaches x2 at time t2, and we want to find out the correlation between these two positions at two different times. And we use the same approach by looking at the different collisions and then the correlations between the number of collisions at these two times. One can compute this thing, and it turns out that this is given by this. It's some constant times minimum of T1 and T2. And it's the same constant that appears in the variance, the same constant that appears in the variance. So this looks like, these two results looks like that it is this motion of this of a single tracer or a single quasi-particle is like a uniformly drifted Brownian particle with some white noise with this d as the strength of the noise. Okay. If we compute 3-point power, then it does not follow this thing. So for 3-point, it does not. Okay. But at least if we look at till 2-point correlations, then it looks like that this one can think of that this motion of these particles looks like a Brownian particle, and if we approximate the motion by a Brownian particle. And in fact, such a conclusion was also obtained by Ferrari and Ola in this paper. And similar stochastic motion has also been predicted for Toda quasi-particles. So Toda is another integrable system in one dimension, and there also you have quasi-particle picture, and you can also ask for the same question, that what is the dynamics of a quasi-particle, and there also this Amol Agarwal has predicted stochastic motion for single quasi-particle. Not only that, it also prescribed some method how to identify quasi-particle and then study the stochastic motion of the quasi-particle. Okay, so this was the result for inhomogeneous background. It's a T, and it's a minimum of T1 and T2. This quantity, this proportional to T and T1 and T2. But one can generalize this result for inhomogeneous case also, like domain wall. And in this case also, it is proportional to T and mean of T1 and T2, but only the prefactor changes. But not only that, you can actually generalize it to any kind of backgrounds. And however, this simple T dependence goes away, and you have some complicated T and T dependence. But here, the same function appears. In the interesting fact is that the same function appears T replaced by minimum of T1 and T2. And in fact, the functions are explicitly given by such integrals. One can show that. And these are the numerical verification of that theoretical result for a different background: homogeneous domain wall, Gaussian background, sinusoidal background. Okay. But okay, so now I come back to the homogeneous case, where you remember that this quantity, the variance goes as T, and the autocorrelation goes as minimum of T1 and T2, and that led us to think that maybe this is a drifted Brownian particle. But the question is, are they correlated? So I looked at the dynamics of one quasi-particle, but if I look at the correlation between two quasi-particles, how do they behave? And one can do the similar calculation, microscopic calculation, and it turns out that this correlation here grows with time. So it again grows linearly with time, and that actually led us to think that these are correlated in an interesting way. And to see that, we look at the variance of the separation between two. So let's say we have two quasi-particles that we label them, and then we look at the separation and the variance of the separation. Okay, now this is the quantity that we look at, and once again homogeneous background, and in this case we find that at small time, so let's say this one moves with velocity u0, and this one moves with velocity v0. So u0 is not equal to v0, and at small time again both of them are individually moving like a Brownian particle. So that's why the separation, and they are not correlated at small time. So that's why just the addition of their two variances But at large time, again, you get a linear growth in the correlation, in the separation. But interesting fact is that if u naught is equal to v naught, in that case, that at large time, this quantity does not grow. It saturates. So initially it was increasing and it saturates. So this means that that initially they start moving like independent Brown particle, but at late time they move like in a coordinated way, such that even though their center of mass diffuses, but their separation doesn't grow with time. So it's like a rigid body type motion. Okay. So we didn't not only find the asymptotics of this behavior in the large T and small t, but we also computed the full scaling function, and this quantity has a scaling behavior, initial separation by t, and we found out the scaling function, which has the right asymptotics which are predicted here. Okay. Okay, so this is the summary of the quasi-particle which I have shown, but now only this part got added to the last summary. So the individually their variance grows as t, their autocorrelation also grows as minimum of T1 and T2, and their covariance also grows as t with this. So this means that maybe these are Brownian particles, but these are not uncorrelated Brownian particles. So they are seems like these quasi-particles are Brownian particles, but they are correlated. Their noise is correlated. Okay, so this led us to think that maybe one can approximately think that the gas, homogeneous gas of Hadrons, is a gas of non-interacting but correlated drifted Brownian particles, and we consider this a gas and try to derive the fluctuating hydrodynamics of the density, phase space densities of these particles. So we define this empirical density, and if you define this empirical density and use this dynamics, and then there are simple calculations which shows that this quantity has this fluctuating hydrodynamics. So you have a drift term, and you have a diffusion term plus a fluctuation that comes, and this noise is correlated. It's delta correlated, but different labels of this noise, which are labeled by velocity, they are correlated. And these two functions are coming from the quasi-particle statistics. And this is the same result that was also obtained by Pablo Ferrari and Ola in this paper. But there is a puzzle. The puzzle is the following. So to understand the puzzle, let us first look at what is the equation of the averaged phase space density. So for average phase space density, there are studies by Herbert and Benjamin, and also before that Boldrigny and Suhov. They showed that this equation, this quantity satisfies this Navier-Stokes equation. Okay. Now, actually, sorry. This average is over initial conditions. You start with some initial state, and then you can average over this initial state. And also, of course, you also have to do some coarse graining. So now if you linearize this equation about the global equilibrium, so let's say you have a global equilibrium plus a small deviation, then you get this equation. Okay. So the linearized equation gives you this part, this equation from the Boldrigny-Suhov, and from the fluctuating hydrodynamics that we got gives you this. And if you compare, you see that this equation has these extra terms, and so this is a puzzle. How this equation has these extra terms, but this equation doesn't. So still now we do not have a very good resolution of this puzzle. In this case, that what we know, we somehow understand where this discrepancy come from, but how to resolve this issue is not clear. Okay, so any questions till? Yeah.
Large times you said they will act like hard particles with big separation. For the particles act like.
No, I said order 1 fluctuations, even though the center of mass fluctuates by order t.
Would that be the same as in this approximate fluctuating equations?
Yes, that's what we used in this approximate here. We use this, the noises are like that only. So we use that correlation. Okay, so now in the second part, I'll talk about correlations in hard rod gas and also tell you how these correlations give some understanding of the results of the quasi-particle statistics. Okay, so first we define the microscopic correlations. Of course, this is a microscopic phase space density, and this is how you define the correlation in phase space. Okay, and one can compute this correlation. So let me here, for simplicity, I'm talking about the density correlations, which is basically the velocity integrations of this correlation, which is the density. Okay, so of course this quantity you can write down in this form, the two moments and the minus the individual averages, and this quantity is proportional to the joint probability that one rod is at x, another rod is at y at time t, and one can again do a microscopic calculation, keeping one rod here, and distribute other rods. And one can do this calculation. It's very straightforward, but the expression is very horrible. It's a complicated expression. I don't expect you to actually put attention in this. But if you plot this expression, you get this nice result. So, and you see that, so the y is fixed here, 1.55. And you see that within order A distance, there is no correlation. It is, and then and then you have this oscillation. Which is like the rod size, the oscillation size is rod size A. So these are microscopic correlations. What about hydrodynamic correlations? Okay, so first we define what is hydrodynamic field. So hydrodynamic field is basically do a coarse grain the density over some space, let's say delta x. And you can choose the delta x to be much smaller than the inhomogeneity scale, but much larger than a rod length. Okay, so this is the hydrodynamic field, and once again you define the hydrodynamic correlation. Of course, these hydrodynamic correlations should be related to the microscopic correlation by this way. Okay, so the first of all I will present two calculations. One is this correlation can be computed from some hydrodynamic fluctuation theory, which is called ballistic macroscopic fluctuation theory. And also for one initial configuration, initial condition, we can compute this quantity explicitly and then compute this quantity and compare the predictions of BFT with the microscopic calculation. And that's what we'll do. Yeah, microscopic correlations are like this, that it decays. So it will be like few A. Few. I mean, correlation length doesn't come with exponential or minus something, but you can say that, okay, maybe this is the correlation length, which will be like few, maybe 3, 4 A, like this. This is the expression. Yeah, probably, yeah. Yeah. And I'm saying that the correlation length will be some 10 times A or something like that. What correction term? This is an exact expression. Even this is an exact expression. You can even compute it for 10 rods also.
No, but it will have some correction 1 by n.
No, there is no correction. This is an exact expression. There is no correction.
No, I mean exact expression for n, but Finesse correction must be there.
I don't understand.
Integrate over the correlation function, you will get the integrated fluctuation, which is 0 for the...
Yeah, it will give you 0. This expression will give you 0.
Oh, that will give you 0?
Yeah.
That you will check?
Yeah.
No, so then it must continue ongoing correction there.
Okay. Okay, so let me first tell you how one can get this thing from a BFT. Of course, this is a hydrodynamic theory, and it's based on some assumptions. So let me first, before going to that, maybe first tell you the step how we can compute this quantity. So this is how I define the hydrodynamic correlation. Of course, I have shown this thing, but to find out the correlation, this simple formula, one can easily see that if you take the derivative with respect to lambda, you can actually get this thing. But the interesting fact is that this is an exact formula. where this average is over the initial configurations, or you can take the corresponding joint distribution at time t also. But we want to compute the hydrodynamic correlations. So let us first look at the global equilibrium, which is homogeneous case. And in this case, it is very easy, because if it is homogeneous, you can, for any initial configurations, if it is homogeneous and global equilibrium, you can always go to the point particle. And point particle will also be another equilibrium. And there you can easily point for point particle densities, you know that this is the 2-time correlation. And once you have that, you can translate it to the rod correlations, and it becomes this. So this is very easy. And in fact, you can use these correlations to find out these statistics that we did from microscopics, use these correlations to get these results very easily. And let me show you where you can use it. So you remember this was the displacement of the quasi particle, but this displacement, this number of collisions from right to left and left to right, you can write down in terms of the densities. This you can easily see that. So this is the number of rods on the left of the quasi-particle at t, and so this should be equal to the number of rods on the left of the quasi-particle at t equal to 0, plus the net number of rods that crossed this in time t. And using this relation, you can actually express this quantity in terms of the densities, and you can see that any moments would involve computing this kind of correlations, right? And so there you can use these correlations, and you can get back these results very easily. But what about, so these results are true only for homogeneous gas. What about inhomogeneous case? And there you really have to use this kind of thing for arbitrary initial state, which has inhomogeneity scale L. And the basic idea is that the fluctuations in the Euler spacetime scale, which is ballistic spacetime scale, essentially originate from the fluctuations that are there in the initial state, which coherently gets propagated to the current positions and the locations by Euler evolution. That is the idea, basic idea that one uses. And also it's more precisely based on these two principles. Maybe I do not have much time to go into these principles, but it's hydrodynamic principle, projection principle, and the principle of local relaxation. So these are the assumptions. So the basic thing is that in the limit of large L, what you want to do, you want to write down a probability distribution for the phase space density function. Okay, and it turns out that in the large L limit, this probability distribution has a large deviation form, and you can identify an action. That is the idea in terms of the rod densities. And once you have that, then any observable you can compute using this thing. So once you have that, so basically what you do, you approximate the exact calculation with respect to the microscopic probability densities by the hydrodynamic probabilities of the hydrodynamic densities. So this is the approximation, and you use that, and that's what was done by Benjamin, Tomohiro, Yoshimura, and Perfetto. What we did is we used the connection to the point particles, and we have provided an alternate formulation of this large deviation theory in terms of point particle densities instead of hard rod densities. So we write another large deviation theory, but in terms of point particle densities, and you have another action in terms of point particle densities, and once again you use such an approximation and compute this kind of correlations. Now, so this kind of expectations. Now remember, in the calculation of the hydrodynamic correlation, one had to do this kind of expectations. So we replace this expectation by these expectations over the fields, and then once you have these expectations are written in terms of path integrals, and you can do saddle point calculations in the larger limit. And once you do the saddle point calculation, it turns out that one can show that this quantity has this kind of scaling behavior, and one can find out the scaling function. Okay, this is the phase space density correlation. Of course, and higher point correlations will also have such scaling behavior, and I will focus on the 0-0 correlation, which is the density correlation. And one can do the same thing for both initial conditions that I have described earlier. And the interesting fact is that in this case we find that there is each correlation has two parts, one local part which is proportional to delta function, and there is another long range part A long range part means because these are x by L scaling, so there is a long range part, like in the non-equilibrium system that you have. Okay, so for this case, we have an explicit expression for this density-density correlation. Here, the local and the non-local parts are not easily visible, but it's there. And this result was also, this thing was also computed previously, but using a different method, and the expression was not so explicit. And here also the expression is even though explicit, but very complicated. However, the situation is slightly better for this initial configuration. Here you can see this thing very explicitly, where you have a delta function part and the long range part, and the long range part has simple expressions. And we have a comparison of this thing from the simulation first. So we did direct numerical simulation of the dynamics, and again do this thing and compute this correlation, and indeed it agrees with the BMFT result. Not only that, we also have compared this from microscopic correlation. This was the microscopic correlation, and we did the coarse graining over the microscopic correlation like this. And there also, this microscopic correlation also gives you the same result, so which is kind of giving a extra validity of the hydrodynamic assumptions that we used into the fluctuating theory, macroscopic fluctuating theory. Okay, so this was for equal time correlation, but we also did the same thing for unequal time correlation. So the results are not yet very good, the simulation results. These are very, very recent results, last week's result. So, but we are improving this result. So, okay, so this brings me to the conclusion that hard-rod system provides a simple yet non-trivial platform to understand various features of generalized hydrodynamics and the fluctuations in because one can study the system both macroscopically as well as microscopically. And one can study quasi-particle dynamics, and it seems to move like effectively like a drifted Brownian motion. And we also have shown that these statistics, the correlations are originated from the hydrodynamic correlations. And such correlations we have computed both microscopically as well as from using macroscopic fluctuation theory, BMFT. And the agreement between these two gives the validity of the predictions of the BMFT. The question is, can one do the similar study for tag particle motion in other integral systems, TODA, or maybe one can use this BMFT to compute other quantities like current fluctuations and maybe full counting statistics. So thank you for your attention.
Okay, questions? Yeah, this.
Yeah, maybe you mentioned already, but again, so you had this approximation in terms of this bias random walk, right, for this quasi-particle dynamics. And if you ignore the correlation between them and just compute the tag particle distribution, the large deviation, does it give, I mean, how does it compare? Is it good or?
No, the large deviation of the tag particle from exact microscopic calculation,
exact microscopic simulation and this biased random walk approximation, because these are non-interacting particles. And then
I see. The large deviation we didn't look at. We looked at only the typical behavior. But yeah, large deviation would be probably different because higher order for single quasi-particle, but higher T correlations are not Brownian. So there are correlations, there are growing correlations, which I didn't talk about, but we found that later.
I see.
Okay. Can you see if the fourth cumulant, it's like higher cumulants are they're non-zero and grow as T's, I guess that must be true.
Three-time correlation we computed explicitly, and it's again minimum of T1, T2, T3 times some coefficient, and that was computed and also compared with the simulation, and it is really, but
Okay.
yeah.
Any other questions? Okay, so if no other questions, let's thank Anupam.